Hey, yeah, good evening, good morning, everybody. So my name is Onno Martens. I am with Trinamic, now part of Maxim Integrated. Yeah, as Ted already mentioned, we've been recently acquired by Maxim Integrated, and we are very happy to join that big family. And yeah, what I would like to present to you is the Rosinante today, which is our motor control SoC with integrated RISC-V core. And maybe a short thing about Trinamic. So what we are actually doing is transforming digital information into physical motion. And how are we doing that? We create, produce, and sell integrated circuits, system in a package, and modules, as well as drives that have a digital interface. For example, for the chip, it could be an SPI interface, and this chip directly drives an electric motor. And our products are highly sophisticated, so we put a lot of intelligence in these products to be highly competitive. And yeah, we want to make life easy for our customers. So ease of use is one of our main drivers, innovation drivers. And of course, we have the same challenges as Bertrand already pointed out. So safety, security also comes to us. But usually we are more on the application level where we want to achieve highest performance out of a very small form factor. Okay, so these chips, for example, usually don't have a processor inside. And the question is, why not integrate a microcontroller into a motor driver? And if we look at some of our solutions, so we actually sell these drives, we call them PAN drives. So we have an electric motor. I don't know, can you also see my laser pointer? Probably yes. So we have an electric motor and we have a PCB where a microcontroller is on and one of our drivers. And you simply plug in power and some digital interface, for example, CAN or UART, RS485 interface, and then you can control this motor. Sometimes you also have a sensor. Here's a magnet mounted on the shaft of the motor, and on the backside of this PCB, you will find a sensor IC. And why not integrate the microcontroller with the motor driver so you have a much more compact solution? Maybe you can even put in some of the discretes or other peripheral chips. And yeah, why doing that? Most people say the microcontroller is much more flexible if you have it separate. And we thought about that, and I would like to show you our conclusion here. So when we start with the motor, and if we want to control this motor, we of course need a power stage consisting of power transistors usually and a pre-driver. And if we put these two components together, we call that a driver. If we add a motion controller, we usually do that in digital hardware, not in software. We have a C driver, so a controller with a driver. Sometimes we also add some position feedback. This is not necessary, but in some use cases, you would like to have that. And this is controlled by an MCU, and this MCU provides some higher level protocol to the host. So for example, a CAN protocol or RS485 protocol. And yeah, and in these things, it's all about integration. Yeah, usually it needs to be small, it needs to fit in a certain space. And so we thought about adding the MCU. And most customers, a lot of people ask us, why do we do this motor control in hardware? And the very basic answer to this is, of course, there is a global trend towards software-defined products. That's for sure, but software changes and physics don't. And motor control is a lot about physics. It's a lot about the motor's physics. It's how you drive the current into the motor. And if you do the software protocol stuff and this motor control stuff on the same MCU, you have a lot of challenges. And one of these challenges is basically taking care of both of these tasks at the same time. Here I have displayed a typical, how to say that, a chart where the typical tasks of this microcontroller are displayed. So usually we are working on our background program somewhere here. And then according to our pulse width, so PWM, we have to do some sort of control algorithm for the motor control stuff. So we step out of our background program and do this motor control stuff, and then we switch back to the background program. And these two tasks are always competing about the resources here. And it could be very hard to find the right microcontroller that actually supports both of these tasks very good, because it needs to fit very different things. So with the communication stuff you have to meet, and also with the motor control stuff you have to meet your specifications. So it's much easier to split this up into a dedicated motion control part where you do this real-time stuff, and a dedicated MCU part where you just do this protocol handling. And by doing that, you also get a lot of advantages. And one advantage I would like to show you is, for example, the current control performance. So with a usual microcontroller, you can achieve a controller update frequency of about 20 kilohertz if you don't want to invest too much money. If you go for a very expensive DSP, you might achieve higher frequencies, but this is the usual case. If you take a hardware solution which does all the control and hardware, you can easily achieve 200 kilohertz. And the step response looks much nicer. You have a faster settling time, the torque follows the system faster, you have a better position stability, and you have a reduced risk of overcurrent. Very nice, and it is basically put inside a dedicated block which is proven and tested and designed by motion control experts. Okay, so going back to this slide, of course, we want to integrate further, and we want to integrate this MCU part for this interfacing to have a very smart and small component. And of course, we used RISC-V, otherwise we wouldn't be here. So why would we choose RISC-V? And our arguments are pretty easy. We like RISC-V because of the flexible choice of extensions. So we can get open source cores, or we can license cores with very different specifications. We see a very nice community of strong supporters. We see a very fast growing ecosystem, and we see that this RISC-V approach is stable and sustainable, because let's say I build an integrated circuit, and after some time the process in which I did my integrated circuit is discontinued. As Trinamic is fabless semiconductor company, we have to deal with that. And with RISC-V, we have the complete RTL sources in our hand, and we can easily transfer to a different process. And that is very helpful to keep our customers calm and actually generate longevity. Okay, so how does our Rosinante look like? So from a top-level view, our processor system of course, contains a RISC-V core. I will get to the specs later. It has an on-chip debugger. We have some integrated memory with non-volatile memory and SRAM. And we have some local bus for our peripherals, and of course we have an interrupt controller, and we have some chip peripherals. So like a basic processor system, nothing really serious. But if we look into the use cases, we see that we have to serve a lot of different interfaces. So we decided to integrate not only a standard CAN controller, but a CAN FD controller with higher data rate. We put in a standard USB interface to give the customer the possibility to do very easy software updates in the field. And of course, we needed some sort of serial interface controller. We have a quad SPI controller we could, for example, use to interface an EtherCAT slave controller, which is an industrial Ethernet, which is very popular in Europe and Asia right now. And also the memory sizes displayed here on the right. So the 128 kilobytes of flash are basically derived from these EtherCAT and CAN requirements for our standard protocols. So sometimes we do CAN open protocol, and there you need a special communication stack, and there that basically determines our flash size. Yeah, and the SRAM can never be big enough, but we decided for 32 kilobytes, and this is quite good. And the question is, what is missing in this block diagram? And that is actually the biggest part we are missing here. That is the motor control part. And this looks basically like this. I start from the right side. So we have the motor, we have the power stage outside. Actually, we have some parts inside of the chip, but this only displays the digital part of the control. So we have a so-called FOC servo controller implemented, FOC for field-oriented control, which is basically the most efficient way of controlling a three-phase or two-phase stepper motor, three-phase BLDC motor or two-phase stepper motor. And for that, we need a certain current control loop consisting of certain controllers, some transformations, and very fancy space vector PWM block. We need to process some feedback from encoders or digital Hall sensors, and there we have a optimized decoder unit here. And we need some controllers for velocity and position of our motor. And to add some benefits for our customers, we also integrated a very nice ramp generator, which basically generates motion profiles, so you don't have to do that in software. Yeah, and if we put that all together, our system takes shape, and it basically looks like this. So we have the RISC-V core in the middle here, the non-volatile memory and the SRAM. Our standard peripherals like the communication interfaces and the serial interfaces, and of course some timers and so on. We have some chip peripherals like oscillator, PLL, and of course here on the power supply we have some switching regulators, linear regulators, whatever you need. And the JTAG interface, we have a lot of GPU, so IOs in general, we can use for various functions. And we integrated very nice analog components. So we have integrated SAR ADCs here and a small gate driver for 24-volt applications. And so customers can easily choose their MOSFETs and use the internal gate driver, and you have a very, very compact solution integrating a lot of functionality in a TQFP 48 housing. So we have one version with TQFP, so with 48 leads, and another one with 64 leads in planning. Yeah, and so this is our very small and smart solution. If we look at one of our early prototypes, this is a photo of the die itself. So we see here the digital part. Of course, this is not size optimized. It was a test design. We have the ADCs here. We have the services block with all the switching with all the voltage regulators. Here we have the gate drivers for external MOSFETs. This is the SRAM block, and this is the flash block, or double EEPROM in this case. And if we look at the digital part, the RISC-V core is really small. So we choose a 3-stage pipeline core. We licensed from CodaSip, a Czech company, a former Czech company. I guess they are now officially located in Munich, Germany. And our memory controller is quite complicated, and our servo controller core takes up most of the area here. And of course, we have the peripherals with the CAN controller, the USB controller, which take up a quarter of the area. Yeah, and in order to move on with the development and have our customers or later customers evaluate the performance, we created this very nice development platform. We call it Doc5, related to RISC-V. And of course, this has an FPGA on it. Rosinante has an FPGA. Some of you might recognize the very nice and shiny spaceship on the housing here. And the later Rosinante IC, so the real ASIC or SoC, will integrate 13 chips we find as discrete ICs on this PCB. So that is the level of integration we are targeting here. So this is, for example, the USB transceiver we will integrate, the gate drivers, the shunt amplifiers, the ADCs, a voltage regulator, and something I've been missing now, but most of it is covered, I guess. And that is actually my last slide. I would like to conclude. So as a company, Trinamic loves RISC-V because of its flexibility, of the applications that open up with it. And we love to be part of this community. And as end users of these cores, we have a great benefit. Delivering really smart and highly integrated products to our customers. And I will be very happy to announce the final product next year, probably. So thank you for your attention.